Okay. So I left you guys yesterday with this problem to try. We were going to evaluate f of 0, f of 7, and f of 9. This is the graph of f prime. And so what we're going to do is we're going to use that and the fact that f of 3 is equal to 5 to evaluate those function values. So f of 0, if we use the fundamental theorem, I want to know 0. I know something about 3, so I'm going to look at the antiderivative from 0 to 3 of f prime of x dx, which is going to be f of 3 minus f of 0. We can evaluate this using area. So the integral from 0 to 3 would be that area, which they've told us is 4. F of 3 is 5. F of 0 is what we're solving for. So then f of 0 is going to be 5 minus 4, so on. For f of 7, we could start back at 0, but I'm going to start at 3 and look at it from 3 to 7 so that I don't have to add this 4 and subtract this 9. So I'm going to look at this as the integral from 3 to 7, f prime of x dx. It's going to be f of 7 minus f of 3. This definite integral will be the area of that region, which they've told us is 9. So the integral is going to be equal to negative 9 because that region is below the x-axis. F of 7 is what we want to know. We know f of 3 is 5. So then f of 7 would be equal to negative 9 plus 5, negative 4. And then finally, this last one, we're looking for f of 9. Rather than going all the way back to 3 and having to subtract this region and add this region, since I already know f of 7, I'm going to start there. And I'm going to look at this as the integral from 7 to 9. F prime of x dx would be equal to f of 9, which I'm looking for, minus f of 7, which I know is negative 4 from the previous step. So the integral from 7 to 9 of f prime will be the area between the curve of f prime and the x-axis between 7 and 9. They told us that area is 2, positive because it's above the x-axis. F of 9 is what I want to know. I know f of 7 is negative 4. So then f of 9 will be 2 minus 4, negative 2. And then they asked us to do something different. They asked us to sketch the graph of f. Well, we have some points, at least, we can graph. We know f of 0 is 1. We know f of 3 is 5. Then we know f of 7 is negative 4, and f of 9 is negative 2. So I'm going to just kind of scale this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. F of 0 is 1, so we'll put a point there. F of 3 is 5. F of 7 is negative 4. 1, 2, 3, 4 is about there. And f of 9 is negative 2. Now they've given us the graph of the derivative of f. And last semester we learned that the graph of the derivative tells us things about the function. What are some of the things that the derivative tells us about the graph of a function and how it's behaving? where the derivative is greater than 0, the function is increasing. And where the derivative is less than 0, the function is decreasing. Whenever the derivative is equal to 0, we have a possible maximum or minimum depending on if the sign of the derivative actually changes where it's equal to 0. Remember, where the derivative is equal to 0, we call that a critical number. So for example, at x equals 3, we have a critical number. Can we be more specific? Do we know exactly what's happening with our function? The derivative changes from positive to negative, so the function changes from increasing to decreasing. Therefore, at x equals 3, our graph has a relative max. What's happening at 7? We have the derivative changing from negative to positive, so our graph has a relative minimum. What about in here at about 1.5? What happens with our derivative? At about 1.5, right here. This relative maximum of the derivative, right here. What happens with our derivative at this point? The derivative changes from increasing to decreasing. If the derivative changes from increasing to decreasing, then the second derivative changed from positive to negative. And if the second derivative changed from positive to negative, then the graph of the function changed from concave up to concave down. So in here, we're concave up, then we're concave down. This point is an, what do we call where we change concavity? The inflection point. It's an inflection point. This is an inflection point. Do you guys see that this would also be an inflection point? Because here our graph changes from concave down to concave up. Also an inflection point. Do you see how we're tying this all together with what we learned last semester? Last semester, we knew where the high points were. We knew where the low points were. We knew the intervals of concavity and the inflection points. We just didn't know how high the high points were, how low the low points were. But now we do, because we know that we can use the area under the curve to figure that out exactly. So for example, we said at 3, that's a relative maximum. We know that that value is actually equal to 5. They gave us that. So in between and about 1.5, I know my graph is increasing because the derivative is positive. I know that it's concave up until 1.5, and then it's concave down. Then I know that my graph is going to be decreasing all the way to this point at 7. I know that it is concave up until about 5. I'm sorry, concave down until about 5. And then it'll be concave up again. So decreasing, concave down until about 5, and then concave up again. I know that at 7 I have a relative minimum, and that after 7 my graph will be increasing again. It's going to be concave up until about 8, and then it's concave down until 9. So that's our sketch of F. You guys have any questions about anything we did there? Fundamental theorem, or all of the stuff about function behavior in the first derivative, where it's positive or negative, being increasing, decreasing, extrema. First derivative also tells us concavity, where it's increasing and decreasing, inflection points, everything we needed we were able to get from that graph now. Yeah, I think that was breakfast. Okay. We are going to use our calculators on the next one, so go ahead and grab your 89s. Or 84s if you want. You can use the 84 on this. 2 bags for 3 people. It's like 2/3 of a bag each. Okay. All right, let's take a look at this last example. It says a pizza with a temperature of 95 degrees Celsius is put into a 25 degrees Celsius room when T equals 0. The pizza's temperature is decreasing at a rate R of T equals to 6 times e to the negative 0.1 T degrees Celsius per minute. Estimate the pizza's temperature when T equals 5 minutes. They've given us a rate of change. And if we integrate the rate of change between 2 points, what are we going to get? The amount of change. And if we know what temperature we started at, and we can figure out the amount of change in the temperature, then we can use that to figure out what the temperature will be in 5 minutes. Does that make sense? If I integrate the rate of change with respect to time, well, this would be our initial condition, right? We're starting at 95 degrees, so we can think of this as the temperature. Maybe we call temperature T at time 0. And we want to know the temperature after 5 minutes, so that would be T of 5. So T of 0 is 95 degrees Celsius. T of 5 is what we're looking for, which means we're going to integrate the rate of change from time 0 to time 5. And that's going to give us the temperature at time 5 minus the temperature at time 0, the amount of change. We good with that setup? So they told us that it is decreasing at a rate of 6 times e to the negative 0.1 T degrees Celsius per minute. It is decreasing at that rate. What do we need to make sure we do? Make it negative, because it's decreasing. So we're going to integrate negative 6e to the negative 0.1 T with respect to time. That's going to tell us the difference in the temperature at time 5. Well, we don't know what that is, but we do know the temperature at time 0 is 95. We're going to use the calculator anyways, because we don't know what the antiderivative of E is. Okay. We don't know what the antiderivative of E is yet. We'll get there. We don't know how to do exponentials yet. Okay, so we are going to integrate negative 6 e to the negative 0.1 t. The e is where the x button is. If you press the second key, you'll get natural log, and if you press your function key, your green key, then you'll get e. Negative 6 times e to the negative 0.1 t with respect to t. You could call it x if you want to, but we actually have a t button, so I'm just using t. Starting at t equals 0 and stopping at t equals 5. Absolutely. Yeah, you can call it X if you want. I use T because there's actually a T button. If it's X, Y, or Z or T, I just use the button. If it's anything else, I usually use X or something. So we get negative 23.60816. So in other words, during that 5-minute time interval, the temperature of the pizza decreased by 23.60806 degrees Celsius. Which means that if we started at 95 degrees and we lost 23.60816, then in 5 minutes the temperature will be 392 degrees Celsius. You could also put 71.391 if you truncated instead of rounding. Wait, you'd put what? Oh, you put 1/8. You just went ahead and did 4 decimal places. That's also okay. As long as your answer is correct, rounded or truncated to 3 decimal places, if you go more decimal places, they just ignore it. So if you put that on the AP exam, they would read that as 71.391 and wouldn't read anything after it, which is perfectly acceptable. That's the whole reason they accept truncated answers on the AP exam, is because if you give a higher level of accuracy, that's fine, but then you didn't round. So it would be unfair to penalize somebody who didn't correctly round and not penalize somebody who went 4 decimal places if you didn't actually check the 4th decimal place for accuracy. That's why they let you round or truncate. That's the logic behind it. Do you have any questions about that one?